Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we will continue with numerical in roving frame. The first one we have already done in the last session, that is we have the bobbin leading roving frame which is running at 1000 rpm spindle speed, which is producing roving of 2.5 turns per inch. The empty bobbin diameter and diameter is given as 5 centimeter, and what we wanted to measure, that is the what is the percentage change in bobbin rpm when the speed changes to 10 centimeter diameter. So, that we have already done. So, we have done detailed calculation in last class, and we have reported, we have observed that the decrease in bobbin rpm was 3%. Okay. That is that was the answer, it was 3%, we got the answer. Now, next numerical, here what is given in a bobbin leading roving frame is the, it is written, it is a bobbin leading roving frame. The empty and full bobbin diameters are 50 mm and 150 mm. Okay. That is the 5 centimeter and 15 centimeter their diameter respectively, and the initial and final bobbin speed rpm, initial rpm was 1318. So, if we see the speed profile, bobbin diameter and the rpm of bobbin, spindle speed is constant. So, we have this profile here. In this profile 2 points are given, the point 1 which is bobbin diameter 50 mm, that is initial diameter 50 mm, and where the speed is rpm, here rpm is 1318 rpm, and the bobbin full bobbin diameter is 150 mm, and the speed has dropped to, it was there and it has dropped to 1106 rpm. Okay. And what is being asked, calculate the twist per meter. So, twist per meter is given by spindle rpm by delivery speed, that is the twist per meter, twist per unit length, but here nothing is given, in S spindle speed is not given and delivery speed is not given, only 2 points are given. Now, we have to calculate first spindle speed, then delivery speed using all the given data. Okay. Now, let us see. So, delivery speed, let us assume the it is V d and spindle speed is N s. So, both this data are absent. So, twist will be N s by V d, that we have to calculate. So, empty bobbin diameter is V D I and initial bobbin diameter, and final bobbin full bobbin diameter is df, and for empty bobbin the relationship, the speed relationship is pi di multiplied by n bi. Bi is the bobbin speed, initial bobbin speed, okay, and that which is given, and minus ns, and for full bobbin pi df n bf minus ns equal to Vd. So, Vd is delivery speed is constant and ns for both the equations are constant. Now, if we with the using these two equations, what we can get is di n bi di multiplied by n bi minus ns, that is the winding speed, winding RPM, n bi minus ns is winding RPM, equal to df n bf minus ns. So, that these two equations where this di df n bi n bf they are given. So, except ns spindle speed, all the data are given in the equation in the question. So, let us put all this data, that means 50 means millimeter diameter and 1316 is the RPM, initial RPM, and 150 is the final diameter and 1106 is the speed, bobbin speed at that, at the end, at that diameter 150 millimeter. Now, solving this equation we get the ns equal to 1000 RPM. So, ns, that means spindle speed is 1000 RPM. Now, we can from this we can get the delivery speed. So, we can take any one of these equations in case of full bobbin or empty bobbin. So, initial stage. So, that we can use this ns in any of the equations to get Vd. So, Vd we can get using the case of empty bobbin. So, we are getting 49.95, okay, that is approximately 50 meter per minute. So, twist per meter will be 1000, that is spindle speed divided by delivery speed 50 meter per minute, that is it will be 20 twist per minute, twist per meter. So, we can use the full bobbin in case of this equation also, the same result we will get. Okay. Now, the next numerical, here a 120 spindle roving frame. So, roving frame has got 120 spindles, this is the standard size, producing 100% cotton roving from 4.87 kilotex combed sliver, okay, and which is running at 96% efficiency. That means, the production efficiency is 96% and combed sliver linear density is 4.87 kilotex, with empty and full bobbin diameters are 50 and 150 respectively. The same data are being used here, and then you have to calculate the productivity of the roving frame in kg per hour. So, this is the relationship. So, that the data which is used here. So, earlier in previous numerical we have used the similar data, same data almost 50 mm and 150 mm and initial and final bobbin speed 1318 and 1106 respectively. So, with this data we have got the spindle speed ns 1000 RPM. So, here also the spindle speed will be 1000 RPM. So, productivity you have to calculate. So, this is the situation here. Now, here the tex of this sliver is 4.87 kilotex. Now, the back zone draft, break draft is 1.11. Here we are talking about 2 zone draft, and main draft is 9.0. So, total draft if we multiply, it will get the total draft. In roving frame, delivery speed Vd, and using the earlier relationship, as I have told, it is Ns, same relationship, we are getting the spindle speed as 1000 rpm and the delivery speed 50 meter per minute, that we have already got, and the total draft becomes break draft and multiplied by the main zone draft, it is 9.9. 9.9 is the break draft, total draft, and roving hank would be, so this is the total draft, and roving this kilotex was 4.87 kilotex, that means it will be 4870 tex. The roving linear density, roving hank in indirect count, it is Ne, it will be 590.5 divided by 4870, 590 and divided by 9.9, because the roving has been stretched 9.9 times. That means, this is a in the roving frame there is a stretch of 9.9. So, effectively roving tex will be 4870 divided by 9.9, and if we want this is tex, and Ne will be equal to 1.20, this is roving hank, it is Ne, this much 1.20 Ne. So, tex this much text 4870 divided by 9.9, tex equal to 5.5 590.5 is the factor. So, we can convert it to roving hank for 1.20 Ne. From there we can calculate directly the productivity of machine, because this is the 1. Here is the, this is the production per machine per kg per spindle per hour. Okay. So, here we will get the one per spindle, we are getting 1.42, because the delivery speed is given, this is the delivery speed, okay, and it is a meter per minute. From there we can calculate 1.0936, we are just converting it to yards per minute, and when we are dividing by 840, we are getting hanks, number of hanks. So, and when we are getting the with the English count, we are getting in pound, this is in pound. Then when you are dividing by 2.204, it we are getting in kg per minute, then we are multiplying by 60, means we are getting kg per hour per spindle, and when we are multiplying it by the efficiency, we are getting the actual productivity per kg in kg per spindle per hour. Now, the whole machine consisting of 120 spindle, the productivity will be 1.42 multiplied by 120, it is approximately 170 kg per hour, okay, per machine. Okay. So, that is the calculation here. Now, next one is that next one is that in a speed frame means roving frame, the lead of bobbin speed over flight speed is 80 rpm. That means, and at diameter of bobbin 7.5 centimeter diameter, the bobbin is leading over the flare by 80 rpm. So, leading over the flare means NB minus NF is given 80 directly, and the diameter at that diameter it says 7 dB is 7.5 centimeter. These are given. Twist in the roving is 50 turns per meter. Determine the bobbin speed when its diameter reaches 12.7 centimeter. First, let us calculate the spindle speed. Okay. From the earlier given data, let us see. Now, lead of bobbin speed over flare speed is 80 rpm. That means, NB minus NF is 80, bobbin diameter 7.5. So, twist in roving is 50 twists per meter and bobbin speed is asked at 12.7 centimeter of bobbin diameter. So, we know this equation V d equal to pi dB bobbin diameter NB minus NS. So, where this is given and this is also given. So, we can calculate directly the delivery speed. So, V d is delivery speed in the front roller of the drafting system, and dB is the diameter of bobbin in meter, and NB is bobbin speed and NS is spindle speed. Now, using this thing we can calculate 80 is directly given, this is bobbin diameter in meter and pi. So, the delivery speed of that roving frame is 18.84 meter per minute, and the spindle speed equal to delivery speed multiplied by twist per meter. We know by from the relationship of twist per meter. So, this is the we can get twist per meter is given, from there we can calculate the spindle speed. So, 18.84 multiplied by 50, it is approximately 942 rpm, that is the spindle speed we have got. Now, we have to calculate the bobbin speed at 12.7 centimeter bobbin diameter. Now, it is easy because we have the delivery speed, we have spindle speed and bobbin diameter is given. So, using this all this data in earlier equation we can get. So, 18.84 is the delivery speed we have got, 942 is the spindle speed we can put here, and 12.7 centimeter means 12.7 divided by 100, it is a meter. So, pi bobbin diameter and NS we can use as 942. So, here NB we can calculate, NB is the bobbin rpm, you can see here. So, 18.84 multiplied by 100 divided by 3.14 pi multiplied by 12.7 bobbin diameter in centimeter, that is NB minus 942. So, we can get the value of NB as 989. So, 989 was the speed of the bobbin, 989. Okay. The roving hank, next numerical, the roving hank 1.6 Ne is produced from 0.16 Ne draw frame sliver with a twist contraction of 1%. So, in a roving frame there is a twist contraction of 1%. The draft change pinion is 40. Calculate the draft constant. So, this is simple. We have the diameter, we have the count. So, from there we will calculate the actual count, then mechanical actual draft, then mechanical draft. From there we can calculate the draft constant. So, here this is sliver 0.16 and here we are getting 1.6 Ne. Okay. So, that means we are getting the actual draft 10. So, actual draft is 10, 1.6 divided by 0.16. Now, the draft, the mechanical draft should be little bit more than that, 1% more than that. So, mechanical draft will be 10.1. Okay. 10.1 is the mechanical draft, and based on that we will calculate the draft constant. So, draft constant is mechanical draft multiplied by draft change pinion. So, we will get the draft constant of that machine as 404. 404 is the draft constant. So, this is a straightforward simple numerical. Let us do another numerical. This is also a very simple one. Calculate the twist per inch on the roving frame if the diameter of back roller is 15 by 16 inch and RPM of back roller is 10. Okay. The spindle speed is 1000 and draft is given as 10 draft. So, there is no slippage, no contraction. So, back roller speed is given, back roller RPM and speed is given. So, they are given, and now we have to calculate the front roller speed. Front roller speed we can calculate using the draft. So, back roller speed, if we calculate pi d of back roller multiplied by n, so of back roller. If we know the back roller speed, then if we multiply by draft, it will be the front roller. Front roller speed. So, if we know the front roller speed and then we know the RPM of the spindle, from there we can calculate the TPI. So, diameter of back roller 15 by 16 inch. So, speed of back roller 10 RPM, spindle speed 1000 RPM. So, total draft 10. Okay. Total draft is given as 10 and TPI. Now, try to see, this is the surface speed of back roller pi d n. So, 29.45 inch per minute. So, surface speed is given. So, draft is 10. So, surface speed of front roller divided by surface speed of back roller. From there we can calculate the surface speed of front roller as 294.5 inch per minute. This is the surface speed of front roller, just multiplying the surface speed of back roller by 10 draft. So, TPI will be surface speed spindle speed divided by delivery speed. So, surface speed of front roller is nothing but the delivery speed. Okay. So, 1000 divided by 294.5, the TPI is 3.4 TPI, twist per inch. Now, let us do another numerical. Now, calculate the number of hours required to exhaust the finisher draw frame can on a roving frame with the following details. Now, if we see the roving, this is the roving frame, and in this can we have total draw frame can weight 16 kg. This is the net draw frame can weight. So, we are talking about the sliver content. Okay. Net now, draw frame sliver hank, this is a sliver hank 0.15 NE, and brake draft at the back zone, the draft is at the back zone, it is a 3/3 system, back zone draft is 1.2 and front zone draft it is 8.33. 8.33 is the front zone draft, back zone draft 1.2, and twist multiplier in speed frame, that means roving frame, is 1.21 and spindle speed is 1400 rpm. Now, these are the data given. We have to calculate the number of hours required to get it exhausted. So, basic thing is that we must know the delivery speed. From there, from the delivery speed, how do you know? So, if we know the twist and spindle speed, so from twist multiplier we can calculate the twist per inch, and then we know the spindle speed, from there we can calculate the delivery speed, and delivery speed is known, and then we know the draft. So, if the draft is D, so take up speed will be V d divided by D, D times lower than the delivery speed. So, here this speed if we know, then we can calculate the time required to pull all these fibers. So, that is one way. Otherwise, what we can do, we can just try to calculate the production, how much time will it take per spindle to produce 16 kg. So, in that way also we can do. Now, let us see the numerical here. Roving hank equal to sliver hank multiplied by draft. Okay. Sliver hank is given. So, roving hank will be 1.5. So, because 1.2 multiplied by 8.33 is 10. So, total roving draft is 10. So, 0.15 multiplied by 10. So, 1.5 NE is the roving hank. So, TPI equal to, because here roving hank was not given. So, we have to calculate the roving hank from the sliver hank. Okay. So, roving hank sliver hank into total draft was given, basically total draft is a brake draft and main zone draft, that we can calculate. Now, TPI is twist multiplier multiplied by under root NE. So, NE is 1.5 for roving. So, TM is given 1.2. So, we can calculate the twist per inch 1.447. Okay. Now, production in kg per hour per spindle, as I have told, this way we can calculate. So, this is the productivity that we have already seen in earlier case also, one numerical. So, this is the RPM of the machine, and from there we can calculate the delivery speed, and then by divided by TPI delivery speed in inch per minute, okay, inch per minute. Then if we divide by 36, it will be yards per minute, divide by 840, that means hands per minute, and 1.5 it give you the pounds per minute, and 2.25 divided by 2.25 it is kg per minute, and if we multiply it by 60 it is kg per hour per spindle. So, that is the in one spindle, from one spindle the in 1 hour, in 1 hour 0.5 kg, 0.57 kg is produced, and how much time will it take to exhaust 16 kg? 16 kg is the draw frame can, 16 kg divided by 0.57. So, approximately 28 hours will be required to get the one whole can exhausted. This is very important in practical sense, because that the balancing, machine balancing will be required. That means, after every 28 hours, more than one day after. So, one that the speed frame cans has to be exchanged. That means, the draw frame productivity in such a fashion. So, we have to exchange that after every 28 hours. The machine balancing should be in that way. Now, another numerical, this is the last numerical probably. So, here we can see this numerical is based on the flat top, and which is a false twist condition we have discussed already. Now, try to see here, a bobbin leading roving frame is running at speed of spindle speed of 1000 rpm with a delivery speed 20 meter per minute. The diameters of roving and the flat top hole are 3 millimeter and 1.8 centimeter respectively. Now, this may not be the actual case, the data, but we can, for our calculation we can assume this is a flat and here it is a flat top and roving is coming. Now, this roving diameter is assumed here, it is 3 millimeter and the flat top it is 1.8 centimeter. Now, if you see here from the top view, this is the flat top, here it is 1.8 centimeter and roving is shown in red color. From the top view this will be like this. This is roving which with a diameter 3 millimeter. Okay. This is the condition, and here the false twist will take place when the flare rotates. This flat top will have the rolling action due to the friction. It will not slide 100%, it will try to roll this roving and the false twist will be imparted. Okay. So, assuming the percentage slip of roving during the rolling, during imparting the false twist is 70%. So, 70% slippage will be there, but 30% will be there for false twist, because there will be, if it can be 100%, if there are the roving the flat top is smooth enough, that can be 100% slippage, but here 70% slippage, but 30% will roll. Now, total twist, that is real twist plus false twist in this zone, in the unsupported zone, okay, the total twist in the moving in the unsupported zone, this unsupported zone there will be real twist plus false twist. Okay. Zone between flat top and the front roller will be. So, we have to calculate the total twist here. So, real twist we can calculate simply by dividing the spindle speed with the delivery speed. So, total twist will be n r plus total twist will be equal to T real twist T will be T r plus T f. So, total twist will be real twist plus false twist. Real twist is imparted by the flare and false twist is imparted by the flat top, that we must be very clear. So, here what in this zone, in the unsupported zone, there will be real twist plus false twist, but after it crosses the flat top zone, the false twist will get cancelled. Okay. And here the real twist will only remain, that means it is the real twist, that here what is the spindle speed by delivery speed, this is the real twist. But what is false twist? Now, let us see. Real twist is T real is 50 twist per meter, the spindle speed divided by the delivery speed. Dia of flat top is 1.8 centimeter, means 18 millimeter. Dia of roving diameter is 3 millimeter. That means, for one revolution, one rotation of the flare, number of rolling will be, so number of rolling of roving per revolution of flare will be 18 by 3 by 6 revolution is supposed to be there. There should be 6 revolution, that is this is, and here is the roving, this is flat top with 118 millimeter diameter and roving with 3 millimeter diameter. So, if it wants to roll and come back to its own position, there will be effectively 18 by 3 6 revolution. If it wants to roll, if it rolls, there will be 6 complete rotation and in that position. Okay. So, it is for one revolution, whole revolution of flare, there will be 6 rotation of the roving, but 70% is slippage. So, only 30% remaining. So, that is why we multiply it by 0.3. So, there will be effective 1.8 rolling action will be there. That means 1.8 rolling means 1.8 false twist will be imparted for one revolution of the flare. So, false twist per flare rotation will be 1.8. That means, twist per flare rotation, the total twist, the one rotation, this is will be there, one twist will be there real twist and 1.8 twist will be there for as a false twist. So, there will be total 2.8 twist per flare rotation. Okay. And we have the speed 20 meter per minute. Okay. And total twist per meter of roving in the unsupported zone will be in 1 meter. This is the twist multiplied by 2.8. So, 1000 divided by 20 that is twist per meter, 1 meter, and one rotation total twist per flare rotation will be 2.8. So, per minute it will be 2.8 multiplied by 1000, and per meter if we want to divided by 20. So, there will be 140 twist per meter in the unsupported zone. Okay. Total twist per meter in the unsupported zone is 140. So, that is what we are looking for, but effectively our in the real twist will be, there will be real twist, it will be 50 twist per meter, which will remain in the roving, but in the unsupported zone there will be very high twist that helps in reduction of the breakage. I think we will stop here. In the initial part of the roving frame, we have understood how the different numerical we can approach with the, we can solve different numerical, how the twist is related with the actual twist, and that real twist and false twist are related with the bobbin speed, and how the bobbin speed changes with the diameter. So, in the next session we will take up a new topic. Till then, thank you.